What do you do when you wake up, glance at your phone, and see a push notification that basically says, James Webb finds a new planet just 4.3 light years away, and then loses it? You tap it, half awake, and there it is in the article, a simple claim that really shouldn't exist in your newsfeed yet. Possible Saturn-sized planet, orbiting in the habitable zone of the closest sun-like star to Earth. But the signal vanished. But before we continue, please subscribe to the channel to give your support. Let's continue. Here's the straightforward version of what happened. Astronomers pointed the James Webb Space Telescope at Alpha Centauri A, the nearest star that looks broadly like our sun. They used MIRI, the mid-infrared instrument, which detects heat, not visible light. They also used a coronagraph, a small mass that blocks out the bright center of the star in the image so the detector can actually see anything faint sitting nearby. In those cleaned images, they saw a point, a small, stable dot of light about 1 to 2 astronomical units away from Alpha Centauri A. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers, or about 93 million miles. So this dot sat somewhere between that distance and roughly twice that, in the same basic range where Earth and Mars sit in our own system. The brightness of that dot in mid-infrared light matched what you'd expect from a cold gas giant similar in mass to Saturn, with a temperature of around 200 to 250 kelvins, well below freezing but still warm enough to glow in Webb's wavelength range. Put simply, the team looked at the flux, the amount of light, compared it to cooling models for gas giants that are a few billion years old, and the numbers lined up with something like Saturn-mass planet at about Earth to Mars distance from its star. At that point, the candidate got a label. Internally, they called it S1. In the usual exoplanet naming style, you'll see it referred to as Alpha Centauri AB, meaning first reported planet around Alpha Centauri A. But crucially, every serious mention of it adds one word: candidate. Not confirmed, not locked in. Candidate. So far, that still sounds like a solid detection, right? A faint dot appears where no dot should be. The brightness makes sense, the separation makes sense, it fits with gas giant models, and the processing pipeline pushes it above the usual 5 sigma threshold, which is the rough statistical standard for this is probably not just random noise. So why isn't everyone simply announcing, we found a Saturn-sized planet next door? Why is this even controversial? Because then comes the part that hurts. The team did exactly what they are supposed to do next. They scheduled follow-up observations. James Webb went back to Alpha Centauri A in 2025, using the same instrument at the same wavelength with the same coronagraphic setup and with even more careful planning, because now they knew exactly where on the detector that signal had appeared. This is how you check if a dot is a real object or just a one-off artifact. The new data came in. They ran the same subtraction methods, removing the star's glare, cleaning up the speckle pattern, searching at the position where S1 had been. And this time, there was no clear point source above the threshold. The dot that was there in 2024 simply did not show up in the 2025 observations. The frames were full of the usual pattern of noise and residual speckles, but nothing that matched S1's brightness and location. Now you're stuck with a tricky situation. One epoch says, there is something. 2 later epochs say, we do not see it. You cannot just ignore either side. You can't pretend the first detection was perfect, and you can't assume the later non-detections automatically erase it. You have to hold both facts at the same time and ask, what does this combination actually mean? Before the team even thinks about claiming the planet is gone, they have to rule out the boring technical reasons. Did the telescope miss point? Did the coronagraph not sit in exactly the same place? Did the instrument warm up or cool down in a way that lowered sensitivity? They go through the engineering logs. They check the pointing, the focus, the detector health. Nothing obvious breaks. There is no "we forgot to turn something on" explanation. Next, they ask whether S1 could have been a background object, like a distant star or a faint galaxy sitting behind Alpha Centauri A that just happened to line up in 2024. But Alpha Centauri A has a large proper motion. It drifts across the sky by several arc-seconds per year. A fixed background source would not stay locked at the same apparent position relative to the star across multiple epochs, the way S1 initially appeared to. That simple geometry makes a background object unlikely. So you're left with three real possibilities. 1. S1 is a real planet, and its orbit carried it into a region where Webb simply cannot see it in 2025, too close to the star or behind the coronagraph's blind spot. 2. S1 is a complex structure in a dust disk, some clump of warm exozygotal dust that happened to look like a compact point in the 2024 data, but changed in appearance later. Or 3, S1 was a statistical or instrumental artifact that slipped through, a rare noise fluctuation or speckle pattern that looked planet-like once and then never repeated. This is where the once-in-a-generation language comes in. If S1 is real, then it is doing something very simple but very important. It is orbiting just 4.25 light-years away, around the nearest Sun-like star to Earth. That distance is about 4 times 10 to the 13th meters, roughly 40 trillion kilometers, about 25 trillion miles. In galactic terms, that's effectively next door. We've never directly imaged the planet in the habitable zone of a sun-like star that close to us. Most directly imaged exoplanets are far out from their stars and far away from us. This would be the closest such world by a huge margin. On top of that, this is one of the faintest planets ever pulled out of a star's glare in the infrared. You're talking about a world that's about 10,000 times dimmer than its host star in Webb's mid-infrared view. To even reach that point, the telescope and the data processing have to push contrast down into the range of 1 part in 100,000 to 1 part in 1,000, at angular separations of around 1 arcsecond, which is a very small angle on the sky. The signal stands only a bit above the noise, at something a little higher than that 5 sigma level scientists like to use as the line between maybe and probably real. So what are you really watching when you follow this story? You're not just watching a yes or no vote on a single planet. You're watching astronomers work at the edge of what the laws of optics and the physics of detectors allow. You're watching them try to separate a tiny stable point from a sea of noise and artifacts with nothing more than photons that left a star 4 years ago and landed on a mirror in deep space. If S1 is confirmed, it forces you to update how you think about the solar neighborhood. Suddenly, there's a gas giant in the habitable zone of the closest sun-like star, and its moons become immediate candidates for best nearby places for life. If S1 does not survive future tests, if it turns out to be dust or noise, it's still a harsh reminder of how difficult it is to claim we have seen another world, when that world is almost completely buried in its star's light. In that case, the story becomes a lesson in humility and method, not in discovery, but it still changes how seriously you take any detection made at this limit. So the real question hanging over you now is simple and sharp, not poetic at all. What kind of star system are we actually dealing with next door? And how many invisible worlds might already be hiding there just below the sensitivity line of our best telescope? What if I told you you don't just live next to one star, you live next to 3, and almost nobody ever thinks about that when they look up at the night sky? Just beyond the icy edge of our own solar system, about 4.25 light-years away, there's Alpha Centauri, and it's not a single star, it's a triple system: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. A and B are a tight binary, 2 stars orbiting each other roughly every 80 years, and Proxima is a tiny red dwarf that orbits far out around the pair on a timescale of hundreds of thousands of years. So your nearest stellar neighbors are not one sun, but a kind of mini star family, a sun-like primary, a slightly cooler companion, and a faint red dwarf tagging along far away. But 4.25 light-years sounds abstract. How far is that in a way your brain can actually feel? Light, which is the fastest thing we know, takes about 4.25 years to cross that gap. In straight distance, that's around 40 trillion kilometers, or about 25 trillion miles. If you tried to drive there at a normal highway speed, say 100 kilometers per hour, about 62 miles per hour, you would need on the order of 45 billion hours behind the wheel. That's longer than human civilization has existed. Even if you upgrade from a car to a fast robotic spacecraft, the numbers are still brutal. Take a very quick probe doing 60 kilometers per second, about 134,000 miles per hour, several times faster than a rifle bullet. At that speed, it would still need more than 20,000 years to reach Alpha Centauri. The only reason this even sounds remotely nearby is because everything else in the galaxy is so much farther away. So here's the paradox. On human scales, Alpha Centauri is impossibly far. On cosmic scales, it's basically next door. If we ever go to another star, this system is the first stop. That means every detail about what lives there, how many planets it has, and what kind of environments they offer matters in a very practical way. That brings up the obvious question. Are there already planets next door, orbiting these stars? And if so, what do we know about them right now? The short, simple answer is yes, at least around Proxima Centauri. Proxima is the faint red dwarf in the system, and it already has at least 2 confirmed planets and 1 more strong candidate. The famous one is Proxima b. It's roughly Earth-massed, just a bit heavier than Earth, and it orbits extremely close to its star, at about 5% of the Earth-Sun distance, around 0.05 astronomical units. It goes around in just 11.2 days. Even though that distance sounds tiny, Proxima is so dim that this orbit puts Proxima b in the star's habitable zone, where the average energy hitting the planet is in the range where liquid water could exist on the surface, if the atmosphere and other conditions cooperate. On top of that, there's evidence for at least 1 more small planet, Proxima d, even lighter than Earth, on a very tight orbit, and a debated outer planet, Proxima c, which might be a gas dwarf further out. The details of C are still being argued over, but the big picture is clear. The little red dwarf in the Alpha Centauri system definitely has planets, and those planets are very close to their star, with orbits measured in millions of kilometers, not hundreds of millions, tucked in tight around the faint, active star that flares a lot. Now, compare that to Alpha Centauri A and B. For years, they looked weirdly empty. People ran radial velocity surveys, precise measurements of how the stars wobble due to orbiting planets. They looked for transits, tiny dips in light as planets pass in front of the star. They even tried early direct imaging. Over and over, they found hints, possible signals, and then those signals fell apart under more data. The most talked about example was Alpha Cen BB, a supposed small planet around B that almost certainly turned out to be just noise in the measurements, not a real world. So, for a long time, the situation was almost ironic. The star that looks like the sun, the one you'd most expect to have a family of worlds like ours, seemed empty. The faint red dwarf, Proxima, had the planets. The bright pair, Alpha Centauri A and B, did not. That's part of why the new James Webb candidate, S1, hit so hard. It's the first serious, directly imaged planet candidate around Alpha Centauri A, and it sits exactly where theory said a nice, big gas giant could live, in the habitable zone, 1 to 2 astronomical units out. So which of these 3 stars is the real main character for you? Proxima has the confirmed planets, but it's a violent red dwarf, throwing off flares and high-energy radiation that could strip atmospheres or sterilize surfaces over time. If life exists on Proxima b, it has to deal with a much harsher environment than Earth does. Alpha Centauri b is interesting, but it's a bit cooler and less sun-like. Alpha Centauri A is the one that really matters for the S1 story. It's the closest real solar twin, a G-type star with a habitable zone stretching from about 1 to 2 astronomical units. In that band, a planet gets a similar overall energy flux to Earth. It's not identical, but it's close enough that the same sort of chemistry and climate possibilities start to make sense. Combine that with the system's distance, just over 4 light-years, and A becomes the best single place in the galaxy to test this specific question. Does the nearest sun-like star have a planetary system that we could, in principle, visit with future technology? And this is where S1 comes crashing back into focus. If that candidate Saturn-mass planet really orbits Alpha Centauri A at 1 to 2 astronomical units, then you suddenly have a giant planet in the habitable zone of the closest sun-like star. Its own atmosphere is probably not friendly to life as we know it, but its potential moons would sit under very familiar sunlight, at distances and energy levels not that different from what we see in our own system's outer regions. Instead of just a triple star system nearby, you're looking at a triple star system with confirmed rocky worlds around the red dwarf and a possible gas giant in the habitable zone of the sun-like primary. So the stage is crowded. 3 stars, multiple known planets, and now a ghost-like giant candidate that might be real, might be noise, and might define what local means for interstellar exploration. The question now is simple. How do you actually see something that faint, that close to a star, from across 40 trillion kilometers without fooling yourself? How do you actually hunt for a planet that is 10,000 times fainter than its star, so close on the sky that it almost sits on top of the starlight? To even try that, you need a machine that is not just a telescope. You need something like James Webb, a 6.5-meter infrared observatory parked 1.5 million kilometers from Earth at the Sun-Earth L2 point, about 4 times the Earth-Moon distance. Out there, it can stay in permanent shadow behind its 5-layer sun shield, cooled down to tens of kelvins, so cold that its own infrared glow does not drown out the faint heat of distant planets and dust. Its mirror, 18 hexagonal segments combined, gives it about 6 times the light-collecting area of Hubble, which means more photons from faint targets and sharper resolution in the infrared. For the S1 search, you use one instrument in particular, MIRI, the infrared instrument. MIRI covers wavelengths from about 5 to almost 30 micrometers, way beyond what your eyes can see. A Saturn-like planet, at a temperature of roughly 200 to 250 kelvins, radiates most of its energy in that mid-infrared band, especially around 15.5 micrometers. That's why the team chose that wavelength. It's where the planet is bright relative to the cold background, but the star is still overwhelmingly brighter. To handle that, MIRI is not just cold, it is extra cold, below about 7 kelvins with its own cryocooler, so its detectors can pick up extremely faint infrared signals without being swamped by their own thermal noise. But even with a cold, sensitive camera, the main problem is obvious. The star is too bright. Alpha Centauri A dominates the image, its light diffracting across the detector in a complicated pattern of rings, spikes, and speckles caused by the mirror segments and support structure. If you just took a raw picture, the planet's light would be buried in that pattern. So MIRI uses a coronagraph, a device that literally blocks the central core of the star's image. In this case, that coronagraph is a special kind called a 4-quadrant phase mask at 15.5 micrometers, and there is also a layup mask at longer wavelengths. When you place the star exactly on the center of that mask, it cancels much of the starlight at the focus, and the residual light is pushed into a ring you can block with a pupil stop. The result is not a perfect off switch for the star, but it can cut the star's brightness by orders of magnitude. On-sky tests show MIRI's coronagraphs reaching raw contrasts of around 1 part in 1,000 close in, and after careful subtraction using reference stars, down toward 1 part in 10,000 to a few times 10,000 at separations under 1 arc second. That contrast number, 1 part in 10,000 or better, is the key. For S1, you want to isolate a source roughly 10,000 times fainter than Alpha Centauri A, at a projected separation of about 1 to 2 astronomical units, which converts to around 1 arc second on the sky at a distance of 4.25 light years. So you are operating right where the coronagraph and the telescope are at their limits. If you can't keep the star perfectly aligned on the mask, if the wavefront of the light isn't stable enough, if the telescope flexes or changes temperature too much during the observation, the residual speckles explode and your contrast collapses. Now look at how the observing campaign is structured. You don't just grab one quick snapshot and hope for the best. You schedule long visits, many hours at a time, and you split those visits into a large set of shorter exposures. Each short exposure records a tiny bit of signal from anything near the star, plus detector noise and background. On their own, they look like a messy, speckled image. But when you align and co-add them, the random noise averages down, while any real, stable source adds up linearly. The result is a final stacked image where something that was invisible in a single frame can emerge as a faint but statistically significant point. In the scenario we're talking about, Webb observes Alpha Centauri A at 3 different epochs over roughly a year, from late 2024 into 2025. The idea is simple. You hit the system once to look for candidates, then you come back twice to see if any candidate moves in a way that matches a planet on a multi-year orbit. Each time, the telescope sits on target for hours. During that whole period, pointing has to be stable at the tiny fraction of an arc-second level, so the star stays centered on the coronagraph and the planet's signal, if it exists, falls on the same detector pixels each time. There's another trick layered on top of this, and without it, you would probably never see S1 at all. Masking the star reduces its light, but the residual pattern of diffracted light and optical imperfections is still there. That pattern, the point spread function, or PSF, is not a simple circle. It's a complex two-dimensional shape with bright and dark patches that change slowly with time as the telescope's optics breathe and shift. To go deeper, you use reference star differential imaging. That means you also observe other stars, without planets as far as you know, that are similar in brightness and color to Alpha Centauri A, using the same instrument configuration. These reference stars give you a template for the coronagraphic PSF under similar conditions. You can then scale, align, and subtract this template from the Alpha Centauri A images. The goal is to remove as much of the star-shaped structure as possible, leaving only residual noise and any extra point sources that don't match the pattern. In practice, this involves trying multiple combinations of reference stars, optimizing the subtraction in different regions of the image, and testing different algorithms to avoid accidentally subtracting away a real planet signal. This kind of PSF subtraction is standard in high-contrast imaging, but Webb, with its segmented mirror and very stable thermal environment, pushes it to a new level. On top of the reference star subtraction, you can also inject fake planets into the data, simulated point sources at various brightness levels and separations, to test how well your pipeline recovers them. If you can reliably recover fake planets at a certain contrast and separation, and you see nothing in the real data at that level, you can say with some confidence that there is no planet brighter than that limit in that region. Conversely, if you see a real point that behaves like the injected ones, with similar noise properties and stability across subsets of the data, you treat it as a serious candidate. Here's what that means for you as a viewer. Every dot you see in a final JWST coronagraphic image is the end product of this entire chain. Precise pointing at L2, a cold mid-infrared detector at around 7 Kelvin, a coronagraph that cuts down the star's light, hours of stacked exposures, reference star PSF subtraction, fake planet injection tests, and statistical analysis to measure how far above the noise a particular source sits. When the team says S1 had a significance a bit above the 5 sigma level in the 2024 data, that number is not coming from a single raw frame. It comes from this entire process. And this is why the tension is so high. Because once you've gone through all that effort, all that careful subtraction and testing, and you still see a point source at about 1 to 2 astronomical units from Alpha Centauri A, 10,000 times fainter than the star, you cannot just shrug and say, probably nothing. At the same time, you know how fragile this regime is, how easily a subtle change in the PSF or a slightly different thermal state of the telescope can create or erase a speckle that looks planet-like. So the next logical step hits you hard, and it's simple, almost brutal. If after all of this you see a dot exactly where a Saturn-mass planet in the habitable zone should be, what do you do when the follow-up data show that dot has shifted, faded, or completely vanished? Is that the orbit of a real planet, or the signature of a false alarm that slipped past every safety check? Before you worry about a planet vanishing, you have to face the moment that started all of this. What do you do when, after all the math and all the subtractions, one tiny dot refuses to go away? You're looking at the final, processed image from the 2024 observing run. The star's glare is mostly removed. The weird diffraction patterns are knocked down. Most of the speckles fade when you change the processing settings, but one point source stays put. It shows up when you split the data in half. It shows up when you change how you subtract the reference stars. It sits at a projected separation that translates to about 1 to 2 astronomical units from Alpha Centauri A, so roughly 150 to 300 million kilometers, or around 93 to 186 million miles. That is basically the range from Earth's orbit out toward Mars. Then you check how bright it is. In the mid-infrared, at that 15.5 micrometer wavelength, the dot is about 10,000 times fainter than the star. That ratio is exactly the kind of contrast you'd expect for a cold gas giant about the mass of Saturn, with a temperature around 220 to 230 kelvins, something like minus 50 to minus 40 degrees Celsius, or minus 58 to minus 40 degrees Fahrenheit. For a distant, sun-warmed gas giant, that is a perfectly reasonable late-life glow. So the next question is simple. Can you turn that glow into an actual estimate of size and mass, or is it too vague? You start with the flux, the amount of energy coming from that dot at that wavelength, and you compare it to theoretical cooling models for gas giants. These models tell you, for a planet of a given mass and age, how bright it should be in the mid-infrared. Alpha Centauri A is a bit older than the Sun, on the order of 5 to 6 billion years, but we're still in the few billion years regime where the planet is old, stable, and slowly radiating away leftover heat from formation, plus what it absorbs from the star. You plug in the numbers. For a separation of about 1 to 2 astronomical units, a planet in that temperature range, around 225 kelvins, lands you in a mass range of roughly 30% of Jupiter's mass. That's about 0.3 Jupiter masses, or a bit lighter than Saturn. The radius comes out in the ballpark of 60,000 kilometers, around 37,000 miles, which again is very close to Saturn's actual radius. There's scatter, there are model uncertainties, but you're not getting something absurd like Earth mass or super Jupiter. You're squarely in the Saturn family. And that's already a big deal, because if this dot is a Saturn-mass world, you know it's a gas giant, not a solid surface planet. Nobody's walking around on it, no matter how nice the stellar flux is. But you also know something else. Gas giants have hill spheres, regions around them where their gravity dominates, and those regions can host moons. For a Saturn-mass planet at 1 to 2 astronomical units from a sun-like star, that hill sphere is big enough to comfortably hold multiple moons the size of Mars or larger, on orbits of a few 100,000 to a few million kilometers, or a few 100,000 to a couple of million miles. Before you go full habitable moon mode, you sanity check the orbit. At 1 astronomical unit from a sun-like star, an orbit takes about 1 year. At 2 astronomical units, it takes close to 3 years. That's just basic orbital mechanics. Farther out means slower, and the period increases with distance. So if this planet is sitting somewhere in that 1 to 2 AU range, you expect an orbital period between roughly 1 and 3 Earth years. That lines up with the idea that, over the gap between the 2024 and 2025 observations, the planet could move significantly in angle but not race around the star multiple times. Then you look at the energy it gets from the star. Alpha Centauri A is a bit more luminous than the Sun, so at 1 astronomical unit, it would deliver slightly more energy than the Sun does to Earth, and at 2 astronomical units, it would deliver a bit less. Somewhere in the middle is a comfortable band where the incoming energy is very similar to what Earth receives. That band, roughly 1 to 2 astronomical units wide, is Alpha Centauri A's habitable zone. S1, based on its projected separation in that first detection, appears to live right inside that band. That's the part that makes your brain stop for a second. You're not just looking at a random giant planet. You're looking at a Saturn-mass candidate in the habitable zone of the nearest sun-like star. The planet itself is not habitable in the way people usually mean. It's a deep hydrogen and helium atmosphere, with no solid surface for oceans or continents. But if you imagine big moons orbiting it, those moons would sit under Earth-like levels of sunlight, with the added factors of tidal heating and the planet's own infrared glow. Suddenly, the region you're analyzing isn't just interesting, it's one of the top theoretical targets for habitable environments beyond our solar system. At this point, you might think the team would just declare victory. The dot's brightness matches a Saturn-mass object, the temperature fits, the location is right in the habitable zone, it shows up in the stacked 2024 data, survives different choices of reference stars, and appears in independent reductions by different analysts. Why not call it a confirmed planet and celebrate? Because this is exactly where experience kicks in. Exoplanet astronomers have been burned before. They know that when you are operating at the contrast limit of your instrument, strange things happen. Speckles line up, noise occasionally imitates a consistent point, and subtle instrument behavior can produce features that look planet-like in one dataset and disappear in another. A single strong epoch is not enough, so they test it as hard as they can right away. They rerun the pipeline with different assumptions. They use different subsets of the data, odd frames only, even frames only, first half of the visit, second half of the visit. The candidate stays. They vary the way they build the PSF model from the reference stars, and S1 stays. These are all good signs, but they still have only one epoch where the signal is clearly above the detection threshold. This is why you keep hearing the word candidate. Even with a detection that looks physically plausible and statistically significant, the team knows they are looking at something right at the edge of Webb's designed contrast performance. They have photons from one time slice and only a very short arc of any possible orbit. They cannot yet watch this world move in a way that nails down a Keplerian orbit. Without that, you don't get to remove all doubt. So the community lands in this uncomfortable middle ground. S1 is not some random glitch. It has survived enough internal checks that people take it seriously. Its brightness and position make sense for a Saturn-mass planet in the habitable zone of Alpha Centauri A. But until you see it again at a different time in a different place that fits a coherent orbit, it cannot graduate from candidate to confirmed. It stays in limbo, an object that might be the most important nearby gas giant we've ever seen, or might be the cleanest, most deceptive false alarm we've hit so far at this contrast level. And that sets up the next step, the one that hurts the most. Because once you have a candidate this good, this close, in this important orbit, the only honest thing to do is go back, stare again, and ask a question that could either unlock a nearby solar system or erase it. When you point James Webb back at Alpha Centauri A and look where S1 should be, what happens if the dot does not come back? What do you do when you run the exact same experiment again with the same telescope, same star, same setup, and the universe gives you the opposite answer? Jump to 2025. You point James Webb back at Alpha Centauri A, same instrument, MIRI, same coronagraph, same wavelength, around 15.5 micrometers. This time, you're not blind searching. You know exactly which part of the detector to watch, because that's where S1 showed up in 2024, about 1.5 arc seconds from the star, corresponding to roughly 1 to 2 astronomical units at Alpha Centauri's distance. You collect hours of data again, you stack the frames, you run the same reduction pipeline that revealed S1 the first time. And in that spot, there is nothing. No point source rising above the detection threshold, just the familiar pattern of residual speckles and background noise. In 2024, there was a statistically strong dot. In 2025, at first pass, it's gone. You don't panic, you also don't celebrate. You start by asking all the boring technical questions, because those are the ones you can actually control. Did the telescope drift off the coronagraph mask more than you expected? If the star wasn't perfectly centered, the star's light pattern changes and your contrast collapses. The engineering team checks the pointing logs. The fine guidance sensors show stable tracking within the tiny fractions of an arc second that MIRI needs. No large drifts, no sudden jumps. Next, you ask if the coronagraph itself behaved differently. Did the mask move? Was there some mechanical or thermal issue? You look at the instrument health reports. Temperatures are in the normal range, the cryocooler is working, the mask mechanism reports the expected positions. You check the detector status. Dark current, hot pixels, read noise. Again, nothing stands out as this would erase a real planet. Webb looks healthy. Then you go after the background object idea. Could S1 have been a faint star or galaxy in the background that happened to line up near Alpha Centauri A in 2024 and then shifted relative to the star by 2025? But Alpha Centauri has a big proper motion. It slides across the sky by more than 3 arcseconds per year. A true background source sits effectively fixed on the sky while the star moves. That means the relative position between the star and any unrelated background object changes significantly from year to year. The detailed analysis in the papers shows S1's 2024 position is consistent with something that shares Alpha Centauri's motion, not something fixed behind it. A background star or galaxy just doesn't fit. So now you're left with 2 broad classes of explanations. 1, S1 is real, but by 2025, its orbit has carried it into a region where Webb cannot see it with this specific coronagraph setup. 2, S1 was never a planet at all, and the 2024 detection was a statistical or instrumental artifact that slipped through all the checks. Both are uncomfortable. Only one lets you keep the dream of a gas giant in the habitable zone of Alpha Centauri A. To decide which way to lean, you have to be precise about what the non-detection actually means. It does not say the planet is gone. What it says is more technical. Given Webb's sensitivity in 2025 at the separations and angles it could probe, there is no point source as bright as S1 was in 2024 at those locations. In plain language, if a planet with the same brightness and separation as the 2024 S1 signal had been sitting in the part of the image Webb could see, you would have detected it. Since you did not, at least one of those conditions must have changed. That is where orbital geometry comes in. Suppose S1 really is a planet with a period of about 2 to 3 years on the kind of eccentric and tilted orbit that fits the combined constraints from Webb and earlier ground-based observations. The published models suggest an eccentricity around 0.4 and an orbit inclined significantly relative to the Alpha Centauri AB binary plane. That kind of orbit means the distance between the planet and the star, as projected on the sky, changes a lot over time. Between August 2024 and the 2025 follow-up dates, the planet could have moved by tens of degrees along its path. Now combine that with the coronagraph's blind zone. MIRI's F1550C mask has an inner working angle of order 1 arcsecond. Inside that radius, close to the star's image, the residual starlight and diffraction pattern make it effectively impossible to see a faint planet. In 2024, S1 was detected at about 1.5 arcseconds, outside that inner limit, where the contrast drops to the 10,000 to 1 level you need to see. But if the orbit carried S1 inward in projected separation by 2025, down to around 1 arcsecond or less, it would slip into the region where Webb is blind with this configuration, even if the planet itself is still physically there, orbiting happily. The team runs simulations of possible orbits that match the 2019 ground-based C1 candidate and Webb's 2024 S1 position, and then ask a simple statistical question. Given those orbits, how often would you expect the planet to be hidden in 2025, either inside the coronagraph's inner working angle or too close to the residual glare to reach the detection threshold? The answer they get is not trivial. One of the papers finds that for a family of stable orbits with periods between roughly 2 to 3 years, there is about a 50% chance that the S1 plus C1 candidate would be missed in both 2025 follow-up observations purely due to orbital motion and geometry. In other words, we didn't see it is fully compatible with it's still there, just in a bad spot. That's the real planet side of the story. The "it was never there" side is harsher, but you can't ignore it. At these contrast levels, speckle noise and imperfect PSF subtraction can create point-like features that pass some of your tests. If conditions in 2024 were just right, you could get a residual speckle that looked stable across subsets of the data and survived changes in the reference star combination. By 2025, with slightly different thermal conditions or wavefront errors, that particular speckle configuration might simply not be present. You run all the internal checks you can, but at some point you have to accept that the noise field is complicated enough that a 5 sigma looking feature in a single epoch might still be a false positive. This is where public headlines and actual data start to diverge. You see outlets using lines like "planet vanishes" or "Webb's biggest exoplanet evaporates." It's catchy, and it feels like a clean story arc. Found, then lost. But that's not what the papers say. The technical conclusion is much less dramatic and much more frustrating. The current data are consistent with two very different realities. Either S1 is a real gas giant on a specific type of orbit that made it invisible to Webb's 2025 MIRI setup, or S1 was a statistical or instrumental artifact, and there is no planet there at all. The observations alone, so far, do not let you choose one with complete confidence. And this is the part you really have to internalize. Even a signal slightly above the usual 5 sigma threshold doesn't feel like absolute certainty when you're working right at the edge of your instrument's design. JWST's MIRI coronagraph is being pushed to contrasts of 10,000 to 1 within about 1 arcsecond of a very bright star. Tiny changes in wavefront stability, mirror alignment, or thermal state can change the detailed speckle pattern. You can do everything right and still end up with one epoch showing a strong-looking candidate and another epoch showing nothing. That's not failure. That is how frontier exoplanet imaging looks in practice. So you're left in a very uncomfortable but scientifically honest place. You cannot say the planet is confirmed. You also cannot say the planet is ruled out. All you can say is that the non-detections in 2025 cut into the phase space of possible orbits and brightnesses, pushing you toward eccentric, inclined 2 to 3 year orbits if S1 is real, and leaving open the possibility that the 2024 dot was a mirage. The heartbreaker is that both options are still on the table. Which naturally leads to the next question, and it's the one everything hinges on now. If a real planet can hide from Webb just by moving along its orbit, what does that orbit actually have to look like in 3 dimensions to make a Saturn-mass world in the habitable zone literally disappear from 1 year to the next? How can a planet big enough to rival Saturn just slip out of sight, without exploding, evaporating, or doing anything dramatic at all? To understand that, you have to stop picturing orbits as flat circles on a whiteboard, and start thinking in 3D. In every textbook diagram, the planet's path is a neat ring viewed from above. In reality, if S1 exists, it's moving on an ellipse that's tilted with respect to your line of sight. You're not looking down on the orbit, you're seeing it from some random angle, and that tilt changes how far the planet appears from the star on the sky, even if its real distance in space stays within the same broad range of 1 to 2 astronomical units. Now add in the limits of Webb's vision. At Alpha Centauri A's distance, about 4.25 light-years, 1 astronomical unit on the sky corresponds to roughly 1 arcsecond, give or take. So the habitable zone, from around 1 to 2 AU, maps to about 1 to 2 arcseconds of apparent separation. The MIRI F1550C coronagraph really starts to work outside roughly 1 arcsecond. Closer than that, the star's residual glare and diffraction pattern make faint planets essentially invisible at the contrasts we care about. In the 2024 detection, S1 sits at about 1.5 arcseconds, roughly 2 AU in projection, just outside that inner dead zone. That's exactly where you want it. But if the orbit carries it inward in projected separation to, say, 0.8 arcseconds by 2025, it drops below the inner working angle. The planet hasn't gone anywhere dramatic in real space, but from Webb's point of view, it has moved behind the star's glare. So when you hear inner working angle, think of it as a hard angular cutoff. Inside that radius, the coronagraph plus the leftover stellar light completely dominate the image. A planet at 0.8 arcseconds that's 10,000 times fainter than the star is not hard to see, it is unseeable in that specific configuration. The 2025 non-detections, combined with the sensitivity maps, basically say if a planet with S1's brightness was sitting outside about 1 arcsecond, we probably would have picked it up. If it moved inside, we wouldn't. That is not hand-waving. That's literally how the contrast curves and completeness maps are built. There's another geometric layer you have to care about, and that's phase angle. At mid-infrared wavelengths, Webb is mainly seeing the planet's own thermal emission, not sunlight reflected off clouds. But that thermal emission is not a perfect, steady bulb. The amount of energy re-radiated toward you changes with the angle between the star, the planet, and the telescope, and with how the atmosphere circulates heat from the day side to the night side. For a Saturn-mass world at around 225 kelvins, climate models and simple radiative transfer calculations say the brightness at 15.5 micrometers can change by tens of percent as the phase angle changes, or as cloud patterns shift. When you are sitting right on the detection limit, a swing of 20 or 30% in flux can move a signal from clearly above threshold to buried in the noise. So combine these effects. S1 sits at about 1.5 arcseconds in 2024, you see it. Over the next year, if its true orbit is something like 2 to 3 years long with decent eccentricity and a significant tilt, its projected separation can shrink under 1 arcsecond at the times you happen to look in 2025. At the same time, its phase angle might shift so you're not catching it at the mid-IR sweet spot for its dayside emission. The planet's physical properties haven't changed. It's not flickering on and off. You've just moved into a viewing geometry where your instrument, with its very specific inner working angle and contrast limit, is effectively blind to it. That's the real planet, bad timing scenario. The orbital modeling in the 2025 JWST papers takes this seriously. They don't just draw one ellipse and call it done. They generate families of possible orbits that fit the 2019 VLT/near candidate C1 and the 2024 JWST S1 detection. Then they run them forward in time and ask, for each of these orbits, where would the planet have been during the February and April 2025 observations, and would MIRI have been sensitive enough at that position to see it? When they overlay those predicted positions on the actual 2D sensitivity maps from the 2025 data, they find that roughly half of the dynamically stable orbits that fit the earlier detections would have put the planet in regions of poor sensitivity both times. In those cases, the non-detection is exactly what you'd expect even if the planet is real. Those same orbit families cluster around periods of about 2 to 3 years with a fairly high eccentricity, around 0.4, and a strong inclination relative to the Alpha Centauri AB binary plane, something like 50 degrees for prograde solutions or about 130 degrees for retrograde ones. That's a very 3D orbit, not a gentle circle. On that kind of path, the projected distance on the sky can swing noticeably over a year or two. There are stretches where the planet sits nicely in the 1 to 2 arcsecond zone where MIRI is powerful, and stretches where it huddles inside 1 arcsecond, where the inner working angle and speckle noise kill your sensitivity. You can turn that into a prediction window. If the period is 2 to 3 years, and if the August 2024 JWST detection really caught S1 near one of its best visible projected separations, then by the time you move into 2026 and 2027, the planet should have swung around to new projected positions where it again sits outside roughly 1 arcsecond for part of its orbit. That is not a random guess. It's a direct consequence of those orbital solutions. The details vary from orbit to orbit, but the general message is give it another 1 to 3 years, then look again with the same or better contrast, and a real Saturn-mass world at those distances and temperatures should come back into view at a predictable set of angles and separations. That's the falsifiable part. If future JWST observations or high-contrast ground-based instruments hit those predicted windows and see a faint mid-infrared source in the right place, moving along a consistent path over multiple epochs, the geometry of a ghost stops being a ghost story and becomes a standard exoplanet confirmation case. You'd have astrometry over a significant fraction of an orbit, photometry at multiple epochs, and a dynamical solution that ties together the 2019, 2024, and later data. At that point, S1 is not a rumor anymore. It's a tracked world. But if you go back in those windows at those predicted separations with similar or better sensitivity and you still see nothing, then the 3D geometry argument can't rescue the planet anymore. A real Saturn-mass world at those distances and temperatures cannot stay hidden everywhere all the time from every configuration that should see it. In that case, the balance of evidence tips hard toward the other explanation. The first planet was never a planet at all. And that brings you to the uncomfortable flip side of this entire story. The one astronomers really hate but can never avoid at this edge of sensitivity. What if S1 is not a cleverly hidden world on a tilted orbit? What if it's just a false positive built out of dust structures and speckle noise that managed to look exactly like a planet once and will never repeat? How many times can the universe cry planet before you stop trusting the signal? Because there's a very real possibility here that S1 was never a world at all. You've seen this movie before, especially around Alpha Centauri. Years ago, there was a big claim of a small planet around Alpha Centauri B called Alpha Cen BB, announced from radio velocity data. It made headlines, Earth-mass planet in the closest star system. Then people started reanalyzing the data with better noise models and the signal collapsed. What looked like a planet turned out to be almost certainly a pattern produced by stellar activity and instrumental noise, not by an actual orbiting world. The planet basically vanished once the statistics got stricter. Kepler did the same thing to the whole field on a bigger scale. It delivered thousands of planet candidates, but a non-trivial fraction of those were later reclassified. Some were eclipsing binary stars whose light curves mimicked planetary transits. Some were background stars in the same photometric aperture. Some were just subtle instrumental artifacts, like rolling band noise in odd pixels. The point is simple. At the edge of detectability, false positives are not rare exceptions, they're expected. Now apply that mindset to S1. One alternative to this is a Saturn-mass planet is this is a dust structure that looks like a planet at JWST's resolution. Think about exozodiacal dust, the extrasolar version of the faint zodiacal light in our own solar system. Our inner system is filled with dust grains, tens of micrometers across, created by asteroid collisions and evaporating comets. They get warmed by sunlight to a few hundred kelvins and glow in the mid-infrared. Alpha Centauri A can have its own version of this, an exozodiacal disk. If that dust isn't perfectly smooth, if it has clumps or density enhancements at around 1 to 2 astronomical units, those clumps can appear as compact bright patches in mid-IR images. At JWST's angular resolution, 1 astronomical unit at 4.25 light-years maps to about 1 arcsecond. A dust clump spread over, say, a fraction of an astronomical unit can still be small enough to look like a point source. Its flux would depend on the dust mass and grain properties, but a hot enough clump could reach roughly the brightness S1 had in the 2024 data. We do have constraints on Alpha Centauri's exozodiacal dust, mainly from interferometry and previous infrared observations. Those studies generally say that Alpha Cen A doesn't have an insanely bright dust disk. It's probably only a few times more dusty than our own inner system, if that. But those are global limits. They don't rule out localized structures that are small and bright enough to mimic a planet at the spatial resolution of MIRI. So S1 is a dust clump stays on the table. It's less exciting than planet, but it's a clean, natural way to get a mid-IR blob at 1 to 2 AU. Then there's the other big troublemaker, speckle noise. Even with a perfectly designed coronagraph, you can't perfectly control the wavefront of light hitting the detector. Tiny imperfections in the mirror segments, small alignment errors, or changes in the telescope's thermal state create interference patterns in the star's residual light. Those interference patterns show up as speckles, little bright spots scattered around the star in the image. In an ideal world, reference star differential imaging would wipe those out. You'd subtract the PSF template built from other stars, and the speckles would vanish, leaving only real astrophysical sources. In reality, the PSF evolves with time. The exact pattern of speckles depends on the telescope's state at the moment of each exposure. If your reference stars don't perfectly match the target's PSF, you'll have residual speckles left over. Now imagine a rare but possible scenario in the 2024 run. The telescope's thermal conditions and alignment combine to produce a speckle that happens to be unusually stable in position and brightness over the observing sequence. That speckle survives when you split the data in half. It survives when you slightly tweak the subtraction parameters. It ends up looking very much like a real, unresolved point source. Its apparent brightness and separation even land near where you'd expect a Saturn-mass planet to be, simply because that's the region where your contrast is best and where you're most sensitive. In 2025, the telescope is in a slightly different state. The wavefront error pattern is different, and that particular speckle configuration never appears. The reference star set is also not identical, so the residual structure in the subtracted images changes. The fake planet from 2024 never reforms. From your point of view, a dot appeared once and never returned. From the telescope's point of view, it was just one realization of a complex noise field. So if dust clumps can fake planets and speckles can fake planets, why isn't the team just saying, okay, fine, S1 was nothing? Why are they still talking about it as a serious candidate instead of quietly burying it? Because even under this harsh scrutiny, S1 passes more tests than you'd expect for a random artifact. It shows up at the same location across different subsets of the 2024 data. If you take only part of the exposure sequence, you still see it in the same place. If you change which reference stars you use to build the PSF model, S1's position holds. That kind of stability is hard to get from a single stray speckle. Its brightness and inferred temperature also line up well with what you'd expect from a Saturn-mass planet at 1 to 2 astronomical units around Alpha Centauri A. It doesn't look wildly too bright or too faint. It doesn't look like a super hot dust lump right next to the star or a cold background galaxy far in the distance. If you feed its properties into standard gas giant evolution models, you get a reasonable mass and radius for an old, sun-like system. Dust-based explanations have to work against that. You'd need a clump with just the right size and temperature to mimic a single unresolved point. You'd also have to explain why that clump doesn't show obvious extension or structure when you push the resolution and signal-to-noise runs in different processing runs. It's not impossible, but it's not trivial either. And yet, all of those pro-planet arguments hit the same wall. They're based on one strong epoch. You still don't have a clear, repeated detection showing S1 moving along a Keplerian orbit, changing position in exactly the way a real planet should change. Without that motion, everything stays stuck in the could-be zone. The false positive sword hangs over the whole thing. That is the uncomfortable balance right now. On one side, S1 behaves in many ways like a real Saturn-mass planet at 1 to 2 AU in the Alpha Centauri A system. On the other hand, you know from history that both this system and this field have a long record of being fooled by seductive signals that disappear under better data and better analysis. You are sitting exactly at that knife edge. Either this is the first directly imaged gas giant in the habitable zone of the nearest sun-like star, or it's another entry in the long list of planets that never were. Which leads naturally to the next round of questions you have to ask, once you've stripped away the cleanest false positive scenarios. If S1 isn't dust, isn't a background object, and isn't an obvious instrument ghost, what else could be throwing you off in the system? And how many more tricks does Alpha Centauri have left before you can finally say planet with a straight face? How do you know the universe isn't just trolling you with some cheap trick from the star itself, or from the background, or from the instrument, instead of showing you a real planet? First thing you do is interrogate Alpha Centauri A itself. Could the star's own behavior fake something that looks like S1? Alpha Centauri A is a G-type star, like the Sun, and all the measurements we have say it's relatively quiet. Its magnetic activity level is similar to, or a bit lower than the Sun's. It has star spots, faculae, all the usual surface structures, but those mainly show up as tiny changes in brightness and radial velocity, not as separate light sources off to the side. In radial velocity surveys, spots in active regions can definitely mimic the tug of a small planet, so you have to be very careful. But in direct imaging, especially with a coronagraph, those features are buried. The disk of the star is blocked, and whatever remains is treated as part of the glare that gets modeled and subtracted. A star spot does not suddenly appear as a lone dot 1.5 astronomical units away from the star in your processed image. It just modulates the total flux of the central source a little bit. So you can basically cross off stellar variability made a fake off-axis planet from the list. The star can mess with your velocities and your light curves, but in this setup it doesn't generate a free-floating blob at 1 to 2 AU. Next, you go after the usual background suspects: distant stars and faint galaxies. At first glance, a small faint galaxy or a background star could easily look like a compact point in mid-infrared images, especially at JWST's resolution. But Alpha Centauri A has a big advantage here. It moves fast on the sky. Its proper motion is over 3 arc-seconds per year. That's huge. Over a few years, it crawls across the background star field by an amount you can measure easily. What does that mean for S1? If S1 were really a faraway galaxy or star behind Alpha Centauri A, that background object would stay put in celestial coordinates. The star, with its large proper motion, would march past it. In images taken years apart, the relative position between Alpha Centauri A and any fixed background object would shift. But when you examine the 2019 ground-based VLT NEAR data and the 2024 Webb data, the candidate appears at a position consistent with something that shares Alpha Centauri's motion, not something fixed in the background. Cross-matching with deep catalogs in that direction of the sky also doesn't reveal a known bright background source that could explain S1 at that location. So the background interloper idea gets weak fast. A true background object would not track with the star's proper motion. S1's apparent position lines up more naturally with something in the Alpha Centauri system, at least in that first detection epoch. Then you look straight at the instrument and ask, are you lying to me? Mid-infrared cameras can produce all kinds of ghosts and quirks. You can get internal reflections off the optics, which show up as faint, offset copies of bright sources. You can get detector persistence, where a previously bright target leaves a temporary afterimage in the pixels. You can get electronic crosstalk, where a strong signal in one part of the detector leaks into another region. All of these can, in principle, produce structures that look like extra spots. The MIRI team knows this, and they've spent a lot of lab time and on-orbit time mapping these effects. Instrument ghosts tend to show up at specific, repeatable positions relative to the bright source and the optical axis. They often have symmetric patterns or predictable shapes. Persistence has known time constants. It fades in a characteristic way with time and depends on the brightness and history of previous observations. Crosstalk shows up along certain directions or readout structures on the detector. So you check S1 against that catalog of bad behavior. Is it sitting in one of the known ghost positions? No. Is it mirrored across the star in a way that matches an internal reflection pattern? No. Does it behave like persistence, getting weaker or changing in a way that tracks the exposure sequence instead of the real astrophysical target? No. Instead, the signal scales with exposure time, appears in subsets of the data, and reacts to processing choices in the way a real external source should. If it were a classic ghost, it would look different. After you've done all that, you strip away what you can confidently blame on the star, the background, or the basic instrument quirks. And surprisingly, none of those easy explanations really fit. Alpha Centauri A's variability can't put a false dot out at 1 to 2 AU in a direct image. The system's huge proper motion makes a fixed background object a bad match. MIRI's known ghost signatures don't line up with S1's position or behavior. So you clean up, that leaves you with 2 serious options, and both are uncomfortable. Option 1, S1 is a real planet, a Saturn-mass gas giant that happened to be in a favorable projected position in 2024 and then moved into a region where JWST's coronagraph is effectively blind during the 2025 follow-ups. Option 2, S1 is an unlucky combination of residual speckles and maybe some small dust structure, a rare noise configuration that survived your tests in 2024 and then never reappeared. In both cases, Alpha Centauri A is teaching you the same lesson. Even with the most advanced space telescope you've ever flown, even with a 6.5-meter mirror sitting in deep space, you are working right at the knife's edge, where discovery and illusion look almost identical. One extra point in the image, one missing point a year later, and you can't immediately tell if you're staring at the first directly imaged gas giant in the habitable zone of the nearest sun-like star, or at a mirage carved out of dust and diffraction. So the tension spikes again. If the obvious red herrings are gone and you're still stuck between planet that moved and noise that fooled you, how big of a deal would it actually be if S1 turns out to be real? What changes, not just for Alpha Centauri, but how you think about nearby worlds and future missions if there really is a Saturn-mass gas giant sitting in the habitable zone right next door? So why are people so stressed about one faint dot around one nearby star when we already know thousands of exoplanets exist? Because if S1 is real, it is not just one more planet, it's basically the jackpot. Start with something simple and brutal: distance. Almost every directly imaged exoplanet you've heard about so far is far away and far out. They tend to be young, hot giants tens to hundreds of light years away from stars, 10, 20, 50 astronomical units from their stars. Great for science, terrible if you care about future missions or anything like, could we ever go there? S1 is a different category. If it's confirmed as Alpha Centauri AB, it immediately becomes the closest directly imaged exoplanet full stop, and the closest known planet in the habitable zone of a sun-like star. You're talking about 1 to 2 astronomical units from Alpha Centauri A, so Earth to Mars distances, but only about 4.25 light-years away from us, around 40 trillion kilometers, roughly 25 trillion miles. On a galactic map, that is basically on top of you. This is the kind of number that mission planners can actually put into spreadsheets without laughing. Next, the nature of the planet itself. A Saturn-mass gas giant in the habitable zone is not where you'd build cities. It's a deep atmosphere, high pressures, probably no solid surface. But dynamically, it's exactly where you'd park habitable moons. With something like 30% of Jupiter's mass, S1 would carve out a hill sphere, the region where its gravity dominates, with a radius of order a few hundredths of an astronomical unit. That's something like 7 to 10 million kilometers, 4 to 6 million miles. Inside that volume, you can fit multiple large moons, each on stable orbits hundreds of thousands to maybe a couple of million kilometers from the planet. That's roughly the scale of our moon's distance from Earth, up to several times that. Now, picture one Mars-size or bigger moon in that zone with enough gravity to hold a thick atmosphere, sitting in a place where the incoming energy from Alpha Centauri A is similar to what Earth gets from the sun. On top of that, you get tidal heating from the giant planet's gravity, which can keep the interior warm, drive volcanoes, maintain a magnetic core, and support a magnetosphere. That combination, Earth-like sunlight plus tidal heating plus a strong magnetic environment, is one of the most serious habitable moon scenarios theorists talk about. It's basically the Pandora setup from Avatar, minus the blue aliens. In our own solar system, you see a weaker version of this with Europa and Enceladus, icy moons heated by tides with subsurface oceans. Take that idea, scale it up, and move it into a habitable zone, and now you have a real target for life that is not a planet at all, but a moon. S1 is exactly the kind of host you'd need. Then there's the observational leverage. Alpha Centauri A is bright, close, and well-studied. A Saturn-mass planet at 1 to 2 AU would tug on the star with a radial velocity signal of a few meters per second, a couple of meters per second at least. That's a change in the star's speed along our line of sight of only a few meters every second, about the pace you walk. But modern spectrographs are brushing up against that precision already, and next-generation instruments are designed to live there. So if S1 exists, radial velocity surveys have a clear, concrete goal: find that wobble. If they see a consistent, repeating pattern with the right period and phase, that backs up the direct imaging data and nails down the mass much tighter. If they see nothing down to that precision, that's a hit against the planet hypothesis. Either way, it's testable. There's also the wildcard possibility: transits. If the orbit of S1 happens to be aligned just right, the planet could pass in front of Alpha Centauri A from our point of view. A Saturn-sized planet crossing a sun-like star would cause a dip in brightness on the order of 1%. For a star as bright as Alpha Centauri A, that is huge in transit terms, and would deliver a ridiculous amount of information. Precise radius, possible cloud signatures, maybe even hints of big moons from transit timing variations, where the timing of each transit shifts slightly because of the gravitational pull of orbiting moons. We don't know if the orbit is aligned that way, and the odds for transits at 1 to 2 AU aren't great in general. But if it did happen, it would be one of the most data-rich exoplanet events possible. A world next door, big enough to block 1% of one of the brightest stars in the sky, with both imaging and radial velocities to back it up. Now, zoom out and look at the human side of this. Emotionally, this hits completely differently from hearing about some hot Jupiter 800 light-years away, skimming the surface of its star every 2 days. Those are interesting, but they feel abstract, like statistics. If S1 exists, your actual sky, the one you see from your backyard, contains a gas giant in the habitable zone of the nearest sun-like star. When you look toward the southern sky and think Alpha Centauri, you're not just thinking binary star system, you're thinking giant planet with possible moons 4 light-years away. That changes how you think about the sun itself. Right now, you can treat our system as a kind of local oddball. Maybe lucky, maybe typical. You don't really know. If Alpha Centauri A, the closest sun analog, also has a giant planet in its habitable zone, that's a huge hint that sun-like stars with wide, stable zones for temperate worlds are not rare accidents. It suggests that solar systems with interesting real estate might be a standard feature of the local neighborhood, not a fluke. It also tightens the connection between exoplanet science and interstellar flight. A Saturn-mass planet at 1 to 2 AU around Alpha Centauri A gives future mission designers a concrete bullseye. You're not talking about launching an interstellar probe toward a generic target and hoping there's something interesting there. You're talking about aiming at a known giant planet with a big hill sphere, where large moons have had billions of years to exist, evolve, and maybe do something interesting chemically or biologically. On top of that, a confirmed S1 becomes the anchor point for everything else in the system. If A has a giant at 1 to 2 AU, what about smaller planets inside? What about additional giants further out? What does that do to asteroid belts, comet reservoirs, and long-term stability? Suddenly, every model of how Alpha Centauri formed and evolved has to include this world. So yeah, if S1 is real, it's a cosmic jackpot. Closest directly imaged exoplanet, closest gas giant in a sun-like habitable zone, best candidate host for nearby habitable moons, the most obvious interstellar target humanity could ever ask for. Which brings you to a harder, more technical question you can't avoid now. If the payoff is this big, why are we still arguing about whether the planet exists at all? And what does this whole mess expose about the limits of our detection methods when we push them this close to the edge? So, what does this whole mess actually teach you, besides space is annoying? It teaches you that at this level, you're not doing a clean see planet celebrate story, you're playing a statistics game on hard mode. When you try to image something like S1, you're sitting exactly where real signals and instrumental noise start to look almost the same. That's why one observing run can pull out a dot that passes all your internal checks, and 2 later runs come back empty. You're not flipping between planet and no planet like a movie plot. You're flipping between slightly different noise realizations, slightly different telescope states, slightly different ways of subtracting the star's light. Each of those tiny changes nudges the signal up or down relative to your detection threshold. In practice, that means direct imaging at this level is mostly math and simulation. You fit models of the star's point spread function. You subtract PSFs built from reference stars. You inject fake planets in the raw data at different positions and brightnesses and see if your pipeline recovers them. You build completeness maps that tell you, at this separation and this brightness, we would detect a planet X% of the time. And then you argue over whether a particular signal really clears the bar. 5 sigma in this context is not a magic number. It's a guideline you try to enforce while knowing that your noise is not perfectly Gaussian and your instrument is not perfectly behaved. S1 sits right in that gray zone. It's bright enough relative to the noise in 2024 that you can't just dismiss it, but not so overwhelming that you can forget about speckles, dust, and processing choices. That's exactly why this story isn't clean. You're working at the limits of what James Webb's optics plus your algorithms can separate from the star's glare. There are 3 hard bosses you are always fighting at once: contrast, inner working angle, and wavelength. Contrast is the brightness ratio between the star and the planet. To see something that is 1 part in 10,000 or 1 part in 100,000 as bright as its star, your optics have to be controlled to insane precision. Tiny nanometer-level errors in the shape of the mirror segments can throw off the wavefront and create speckle patterns that eat into your contrast. You need the coronagraph to knock down the star as much as possible. Then you need your PSF modeling to clean up what's left. Inner working angle is the angular radius inside which the coronagraph and residual starlight basically blind you. There is a hard floor on how close to the star, in terms of angle on the sky, you can see a faint companion as far as that instrument configuration is concerned. For MIRI, at around 15.5 micrometers, that inner working angle is roughly 1 arcsecond. That lines up with about 1 astronomical unit at Alpha Centauri's distance, so the habitable zone sits right at the edge of what you can probe. Wavelength controls your physical resolution. The longer the wavelength, the fuzzier the image for a given mirror size. At 15.5 micrometers with a 6.5 meter mirror, your diffraction limit is on the order of a few tenths of an arcsecond. That's good enough to separate 1 to 2 astronomical units at 4.25 light years, but not much finer. You can't resolve a moon, you can barely pick out a planet from the star's pattern. S1 happens to land in a sweet spot where its thermal emission is strong and the resolution is just enough, but you have practically no margin. Those 3 factors, contrast, inner working angle, wavelength, are not things you can wish away with more enthusiasm. They are baked into the physics of light and the hardware you launched. That's why "we saw it once and then not again" is not a total shock. When you live this close to your performance limits, small changes in any of those parameters or in telescope stability can change what you can and cannot see on a given day. This is also why you can't lean on just one method and call it done. JWST's direct images by themselves give you a position on the sky and a rough brightness. That's it. They don't give you a precise mass. They don't automatically give you an orbital period. They don't tell you what the atmosphere is made of. To turn candidate into confirmed, you need to bring in other tools. Radial velocity measurements tell you how much the star is wobbling along your line of sight, which constrains the planet's mass. Astrometry, ultra-precise tracking of the star's position on the sky, tells you how the star moves in 2 dimensions as the planet orbits, which constrains the orbit shape and inclination. Direct spectroscopy, whether with JWST or future telescopes, can give you actual absorption features from the planet's atmosphere, telling you about methane, water vapor, ammonia, and clouds. No single technique is bulletproof. Radio velocities can be fooled by stellar activity. Astrometry can be contaminated by systematics and calibration errors. Imaging can be tricked by speckles and dust. But when 2 or 3 independent methods converge on the same answer, same orbital period, same rough mass range, same sky position as a function of time, the chance that you're chasing a ghost drops hard. The Alpha Centauri case is basically a live demonstration of that rule. Imaging alone got you S1. Now you need RV, astrometry, maybe even future direct spectroscopy to either back it up or kill it for good. The deeper, slightly uncomfortable lesson here is that the universe does not owe you clarity just because you built a very expensive telescope. At the frontier, certainty is rare and often temporary. Think about early 20th century astronomers arguing about whether spiral nebulae were little gas swirls inside the Milky Way or full separate galaxies. The data sucked by modern standards. People fought over the interpretation. Eventually, better instruments and better distance measurements settled it, and those old maybe objects turned into the galaxies we talk about today. You are in a similar place with S1. Right now, it lives in the maybe bin. It could end up as the first confirmed gas giant in the habitable zone of the nearest sun-like star, or it could end up as a neat case study in how a statistically strong-looking detection still died when more data arrived. Both outcomes are realistic. So you have to get comfortable with this. At the bleeding edge, you move forward by stacking maybes, building better tools, and then going back to retest the oldest claims. Today's candidate is tomorrow's headline, or tomorrow's correction. You don't get guarantees, you get probabilities, tension, and a lot of reanalysis. Which raises the next obvious practical question. If JWST alone can't settle this, who's going to help? What future telescopes and instruments are lining up to either finally catch S1 in the act or prove once and for all that Alpha Centauri A's vanishing planet was just noise pretending to be a world? If JWST alone can't close the case on S1, who's actually going to step in and either save this planet or kill it for good? The key thing you need to accept is nobody's betting everything on one telescope. JWST is the first big move, not the last. Coming next is NASA's Nancy Grace Roman Space Telescope. Roman will also sit out at the Sun-Earth L2 point, but it's built to attack a different part of the problem. It carries a cutting-edge coronagraph instrument that works at visible and near-infrared wavelengths, designed specifically to demonstrate extreme high-contrast imaging of nearby stars. It aims for starlight suppression down to roughly 1 part in a billion at small angular separations, and it can resolve companions as close as about 0.15 arc seconds out to around 1.5 arc seconds. For a planet like S1, that matters because Roman would see reflected starlight, not thermal glow. The planet would be much fainter relative to the star in visible light than in mid-infrared, but Roman's sharper angular resolution and extreme contrast could, in principle, pick out a cool giant at 1 to 2 astronomical units around a nearby sun-like star. You'd then combine that Roman reflected light image with JWST's mid-infrared thermal image. One gives you how much starlight the planet reflects. The other gives you how much heat it emits. Together, they constrain the planet's atmosphere, clouds, and energy balance in a way no single telescope can. On the ground, the next wave are the extremely large telescopes. Literally, the ESO Extremely Large Telescope in Chile will have a 39-meter primary mirror. That's gigantic compared to current 8 to 10-meter class telescopes. With extreme adaptive optics correcting the atmosphere hundreds of times per second, ELT will deliver images in the near-infrared that are more than an order of magnitude sharper than Hubble's invisible light, and with far more light-gathering power. For nearby systems like Alpha Centauri, instruments like METIS on ELT are expected to be able to probe inside 1 astronomical unit and even search for Mars-sized or larger planets in the habitable zones of the Alpha Centauri stars. That kind of resolution and contrast from the ground means you can attack S1 from another angle. JWST sees thermal emission in the mid-infrared. ELT will hit high-resolution near-infrared, where the speckle pattern behaves differently and where adaptive optics can carve a very clean dark hole around the star. If both JWST and ELT see a source at the same location and see it move consistently over time, the chances of it being a noise artifact drop dramatically. If ELT sees nothing down to a well-defined limit where S1 should be bright enough, that's strong evidence against the planet hypothesis. And it's not just about taking pictures. The new generation of spectrographs on these big telescopes are being built to do radial velocities at the tens of centimeters per second. That's about the speed of a slow walk. For Alpha Centauri A, a Saturn-mass planet at 1 to 2 astronomical units would create a stellar wobble of a few meters per second, well above that floor. So future RV campaigns on large telescopes have a clear, precise target. Either detect the wobble with the right period and phase, or set an upper limit that starts to squeeze S1 hard. Astrometry joins in as well. Space missions and dedicated concepts like Toliman are designed to measure tiny shifts in a star's position on the sky at the micro-arc-second level. For Alpha Centauri A, the reflex motion caused by an Earth-mass planet in the habitable zone is a couple of micro-arc-seconds. A Saturn-mass planet would produce a much larger signal, easier to pick up. If you can measure those shifts over several years, you get a direct map of the star's orbit around the system's center of mass, which means a precise mass and orbit of the planet. That's exactly the kind of cross-check you need for something as controversial as S1. So what about timing? This isn't a maybe in 100 years kind of problem. JWST is already operating. The Nancy Grace Roman Space Telescope is currently targeting launch around the late 2020s, with its coronagraph acting as a technology pathfinder for future full-blown habitable planet imagers. The ELT is under construction in Chile right now, with first light expected in the next few years. The 30-meter telescope's future is less certain because of funding and site issues, but even without it, ELT plus other large facilities like the Giant Magellan Telescope will push high-contrast imaging, RV, and spectroscopy forward fast. Realistically, that means this isn't some distant mystery your great-grandchildren will solve. Within a human career, and very possibly within the next decade, you'll have multiple independent datasets on Alpha Centauri A, deeper JWST imaging at better orbital phases, ELT high-contrast images, tighter RV limits, and ultra-precise astrometry. Either they will all start lining up on a consistent Saturn-mass planet at 1 to 2 astronomical units, or they will systematically fail to see anything where S1 should be. In one case, the vanishing planet becomes the first confirmed gas giant in the habitable zone of our nearest sun-like neighbor. In the other, it becomes the textbook example of a false positive at the edge of detection. Either way, the cavalry is real. The tools are coming online, and the clock is ticking on S1's mystery, which raises another, more uncomfortable question that astronomers are already wrestling with. What happens to your trust in "we found a planet, never mind it wasn't real" announcements when you know there's a long history of planets that never made it past the follow-up stage? And how do you turn those failures into something that actually makes future discoveries more reliable, not less? How weird is it that "we found a planet, never mind it wasn't real" is not a rare mistake? It's basically a tradition in astronomy that you're now part of. Go back to the 19th century. Astronomers thought they'd found a planet called Vulcan, orbiting inside Mercury's orbit. Mercury's path around the sun didn't quite match what Newton's gravity predicted. Urbain Le Verrier, the same guy who successfully predicted Neptune, argued there had to be another planet closer in, tugging on Mercury. People even claimed to see it crossing the sun. For decades, observers reported little black dots on the solar disk and said, "There it is, that's Vulcan." Then Einstein published General Relativity in 1915, showed that Mercury's orbit could be explained by space-time curvature near the sun, and the need for Vulcan just disappeared. No extra planet, just better physics. Vulcan went from real to never existed without leaving anything behind except papers and embarrassment. Fast forward to Alpha Centauri itself. In 2012, a team announced Alpha Centauri B, an Earth-mass planet supposedly orbiting Alpha Cent B every 3.24 days, detected via radial velocities. It sounded huge, an Earth-mass world in the closest stellar system, but later reanalyses, using better models of stellar activity and noise, showed the signal was almost certainly not a real planet. The pattern could be reproduced by a combination of sampling effects, star spots, and noise in the HARPS data. Follow-up work basically said, this is very likely a false positive. The planet quietly slid off most official lists. And this doesn't just happen in one-off cases. NASA's Kepler mission, which stared at over 150,000 stars looking for tiny dips in brightness, produced thousands of planet candidates. That word, candidate, is doing a lot of work. Detailed studies have shown that on the order of 10% of those candidates are false positives overall, with higher false positive rates for big planets that are actually grazing eclipsing binaries or blended background stars. Some analyses find global false positive rates around 9%, with giant candidates peaking closer to 18%, mostly due to eclipsing binaries and blended light in Kepler's fairly large pixels. Kepler's team had to learn this the hard way. Early on, a transit-like dip in starlight plus a decent signal-to-noise ratio looked very promising. Over time, they realized you need a whole gauntlet of tests. Centroid analysis to see if the light dip is coming from the target star or a background neighbor, models of eclipsing binaries and triple systems, follow-up spectroscopy from the ground, and later, tools like statistical validation that combine all available information. Only after a candidate survives that entire process does it graduate to confirmed planet. That mindset feeds directly into how people are treating S1. Nobody serious wants to repeat the Alpha Centauri BB situation or the early Kepler false alarms. So by default, S1 is a candidate, not a confirmed world. And the assumption is, it might be real, but we have to act like it isn't until it survives every test we can throw at it. That's not pessimism, that's just learned behavior from decades of being burned. Here's the part that's easy to miss. A retracted planet is not actually a failure of science. It's a sign that the system is working. Every time you kill a false positive, you're forced to sharpen your tools. You improve your noise models. You refine your statistical tests. You build better simulations of what the instrument does under different conditions. You learn how stellar activity sneaks into your data. You make your pipelines more suspicious and your significance thresholds more honest. When Alpha Centauri BB fell apart, it wasn't just a loss. It triggered more careful analyses of radial velocity datasets, new approaches to modeling stellar activity, and stricter standards for declaring tiny signals planets. When Kepler culled its list, the community built automated vetting pipelines that now catch many false positives before they even go public. The end result is simple. The planets that survive this higher bar are more trustworthy. Even if S1 dies, it will force a deeper look at high-contrast imaging systematics around bright nearby stars, which will make later detections in the Alpha Centauri system more solid. But from the outside, the emotional whiplash is real. The public hears, "We found an Earth-mass planet around Alpha Centauri B," and then a few years later, actually no, that signal was noise. They see headlines about possible planets, then about vanishing planets, and it can feel like scientists are just flip-flopping. From the inside, though, this is just what working at the detection limit looks like. You start with candidates, you test them, you upgrade your models, and some live while others die. That's exactly what's happening with S1. The vanishing planet storyline isn't a scandal, it's an example of the process doing what it's supposed to. You got a strong-looking candidate in 2024, you went back in 2025, the follow-ups didn't match the simple, stable dot picture. Instead of brushing that under the rug, the teams publish detailed analyses that say, in plain terms, this either means the planet moved into a bad geometry for detection, or the original signal was a false positive, and we can't yet say which one is right. That's not failure, that's transparency. So yes, the back and forth can be frustrating. One year you're talking about a Saturn-mass giant next door, the next year you're talking about orbital geometry loopholes and speckle noise. But that's the cost of pushing your instruments to the absolute edge of what they can do. If you insisted on only announcing planets that are so easy to see no one could ever doubt them, you'd miss almost all of the interesting ones. And this sets up the next big question you can't avoid. If S1 does turn out to be real, and it really is sitting just 4 light-years away, what does that mean for actually going there? Not just staring at pixels on a screen, but with hardware. How close are you really to turning Planet Next Door into mission target? And what does the travel math actually look like when you stop hand-waving and start counting kilometers and years? If this thing is real, sitting 4 light-years away in the habitable zone, the obvious question is, could you ever actually go there? Not just stare at pixels on a screen. Start with the blunt travel math. Alpha Centauri A is about 4.25 light-years away. In straight distance, that's roughly 40 trillion kilometers, around 25 trillion miles. A Voyager-style probe cruising at about 17 kilometers per second, roughly 38,000 miles per hour, would need on the order of 75,000 years to get there. That's longer than the entire history of agriculture on Earth. For anything like a mission you can plan in a human time frame, that speed is basically standing still. So you push the speed up in your head. Imagine a very advanced mission, maybe nuclear-powered, maybe using fusion, maybe using a beamed sail that can get to 20% of light speed. Light travels about 300,000 kilometers per second, so 20% of that is about 60,000 kilometers per second, roughly 37,000 miles every single second. At that speed, the 40 trillion kilometers to Alpha Centauri turns into just over 20 years of flight time. That's still huge, but now you're talking about a timescale that fits inside one human career, not a whole geological era. Those numbers are not fantasy. They're exactly the range that concepts like Breakthrough Starshot talk about. Starshot's idea is brutally simple. You build a massive ground-based laser array, you aim it at a very light reflective sail attached to a wafer-scale probe that weighs just a few grams, and you hammer it with light until it's going a significant fraction of light speed. The sail gets insane acceleration, thousands of G or more. But because the payload is so tiny, in principle, you can push it to that 20% light speed regime. At that point, Alpha Centauri turns into a 20-year trip instead of a 75,000-year one. You wouldn't ride on that first generation of probes. There's no room for humans, no radiation shielding, no life support. These are chip-sized spacecraft, carrying cameras, sensors, and a transmitter. But if one of them survives the launch, the dust impacts, and the radiation environment, it can, in theory, fly through the Alpha Centauri system and send back images and data. By the time the signals get back at light speed, you're looking at maybe 40 years from launch to first close-up pictures of S1 and any moons at resolutions we currently only get for the outer planets in our own solar system. Suddenly, seeing the planet next door means something very literal. Now think about what changes if S1 is confirmed before you design that mission. Right now, an interstellar probe to Alpha Centauri would be a fly through the system and see what we find mission. You'd have to design very general instruments, spread your attention between Alpha Centauri A, B, and Proxima, and hope you pass something interesting at the right distance and angle. It's like throwing a dart at a wall in the dark and hoping you hit a target you can't see. If you know there is a Saturn-mass gas giant at 1 to 2 astronomical units around Alpha Centauri A, that changes everything. You now have a bullseye. You know roughly where along the orbit the planet will be at a given time. You know its rough temperature. You know its approximate mass. You can design a trajectory that crosses its orbital path at a useful distance. You can choose instrument bands that match the planet's thermal and reflected light spectrum. You can add magnetometer payloads tuned for giant planet magnetospheres and imagers built to detect large moons in reflected light. Instead of a generic Alpha Centauri system survey, you can plan, get within X million kilometers of S1, map its cloud bands, and look for moons down to Y kilometers in size. The mission shifts from blind reconnaissance to a targeted flyby. For engineering, that is a huge shift. You are not just hoping there's something worth seeing, you're aiming at something you already know is there. Even for slower missions, like a big nuclear electric probe doing maybe 10% of light speed, a known gas giant in the habitable zone gives you a reason to spend the money. Remember, even 10% of light speed is still 15 to 20-year travel times, plus 4 years for the data to get back. That's a level where agencies or long-lived private foundations can realistically say, if we start this now, someone alive today will see the results. A confirmed S1 makes it much easier to justify that kind of investment. Of course, all the ugly problems of interstellar flight don't go away just because the target is exciting. You still need a ridiculous amount of energy. Pushing even a tiny probe to 20% of light speed takes more energy than most countries use in a year. You have to deal with dust and gas in interstellar space. At those speeds, a grain of sand hits like a bomb. You have to shield the electronics or design them to tolerate a constant barrage of high-energy particles. You have to figure out how to communicate across 4 light years with a tiny transmitter and a sail that may not be aimed perfectly at Earth anymore. But notice how the framing changes. With no concrete target, those problems feel like science fiction. With a Saturn-mass gas giant in the habitable zone of a sun-like star, they turn into engineering problems with a payoff. You can put numbers on the science return. You can say, if we solve X, Y, and Z, we get direct images of a nearby giant planet and its moons, and we get in situ measurements of a completely different planetary system. That is how impossible missions start, by turning what if into if we do this, we get that. So if S1 is real, it becomes the closest thing humanity has ever had to a true interstellar mission objective. 4 light years is still brutal, but it's not infinite. 20 years at 20% of light speed is still long, but it's not 75,000 years. The gap between totally out of reach and insanely hard but technically thinkable is exactly where interstellar travel starts moving from pure sci-fi into the outer edge of real engineering. But before you start sketching laser arrays and fusion drives, there's one more angle you cannot skip. If S1 really is a Saturn-mass gas giant in the habitable zone, the most interesting real estate in that system probably isn't the planet itself, it's whatever is orbiting it. So what would life actually look like, not on the giant, but on a big moon of a vanishing world 4 light-years away, under Earth-like sunlight and a permanent view of a striped giant in the sky? What does life next door actually look like if the main real estate isn't the planet, but a moon orbiting a gas giant that sometimes disappears from our images? Start by sketching something specific in your head. Take S1 as a Saturn-mass planet and now park a big moon around it, somewhere between 10 and 20 planetary radii away. For a Saturn-sized world, that puts the moon at roughly 600,000 to 1.2 million kilometers from the planet, around 374,000 to 745,000 miles. That's similar or a bit larger than the Earth-Moon distance. It's well inside the planet's hill sphere, the region where the giant's gravity dominates over the star's gravity, so the orbit can be stable for billions of years. Now place that whole setup at 1 to 2 astronomical units from Alpha Centauri A, so the incoming energy from the star is in the same ballpark Earth gets from the sun. The sunlight surface sees a steady stream of starlight, plus an extra bit of infrared glow from the giant planet itself, plus tidal flexing as it orbits in the planet's gravity. Sunlight gives you basic warmth. The planet's thermal emission adds a small bonus, especially on the side facing the giant. Tidal flexing, if it's in the right range, gives you long-term internal heating. You've basically stacked 3 different energy sources in one place. Tidal heating is where things get dangerous and interesting. If you have too little, the moon ends up like our moon, geologically dead, with a solidified interior, no plate tectonics, and a very weak or non-existent magnetic field. It cools down, freezes internally, and any early atmosphere leaks away over time. Life, if it ever starts, has no long-term geologic engine to help recycle carbon or maintain a stable climate. If you have too much tidal heating, you get something like Io. Io orbits close to Jupiter, and Jupiter's gravity pulls and squeezes it as it moves on an eccentric orbit. That constant flexing melts the interior and drives extreme volcanism. Lava lakes, sulfur plumes, huge heat flux. That's great for geology, but probably brutal for anything fragile on the surface. You can imagine an Io in the habitable zone as a world with a sky full of volcanic ash and constant resurfacing. That's not the quiet, stable environment you usually picture for long-term complex life. The sweet spot is in between. You want enough tidal heating to keep the interior warm and partially molten to keep plate tectonics and a liquid outer core running for billions of years, but not so much that the entire surface is a lava field. A Saturn-mass planet at 1 to 2 astronomical units from Alpha Centauri A gives you exactly the kind of mass and distance scales where that balance is possible. The planet's gravity is strong enough to flex a moon, especially if there are resonances with other moons to maintain a slight orbital eccentricity. But the orbital period and distance don't force insane Io-level tides by default. If your moon has at least Mars-level mass or higher, it can hold on to a real atmosphere for billions of years. Mars is about 6,700 kilometers across, just over 4,000 miles, and even it kept an atmosphere for a long time before losing most of it. A larger moon, closer to Earth size, could keep a thick nitrogen-oxygen atmosphere or something chemically different but equally robust. With stable gravity and continued internal heating, it can maintain volcanoes, recycle gases through a carbon cycle, and support a magnetic dynamo in its core. That magnetic field would help shield the surface from charged particles. Now, add the giant planet's own magnetosphere. A Saturn-mass world with a strong magnetic field carves out a huge magnetosphere in the stellar wind. A moon orbiting inside that bubble would sit in a partly shielded environment. The magnetosphere would deflect a lot of high-energy particles from the star, reducing radiation at the moon's surface. At the same time, it would funnel some charged particles along field lines into the polar regions, creating powerful auroras. So you end up with a world that might have relatively gentle overall radiation levels, but intense, permanent light shows in the sky near the poles. And unlike many habitable zone exoplanets around dim red dwarfs, which sit very close to their stars and get hammered by flares and strong UV and X-ray bursts, a big moon at 1 to 2 AU around Alpha Centauri A lives in a quieter environment. A G-type star at that distance has a UV and X-ray environment closer to what Earth experiences. It's not harmless, but it's not the extreme atmosphere-stripping regime you see for many close-in planets around M-dwarfs. That calmer setting gives biology more time to adapt and evolve without constantly resetting the surface with giant flares. From the moon's surface, the giant planet would loom huge in the sky, many times bigger than our moon looks from Earth. Its phases would change as you orbit, and its shadow would cause regular eclipses. Tides in the oceans, if the moon has oceans, would be driven both by the star and by the planet, creating complex tidal patterns. Day-night cycles would be set mainly by the moon's rotation, but the presence of the giant in the sky would add another layer of rhythm to the environment. All of this paints a picture that feels almost too good. Earth-like sunlight, extra tidal heating to keep the world geologically alive, shielding from a magnetosphere, and a stable orbit far from the most violent stellar activity. It looks like an almost ideal setup for long-term habitable conditions. So the obvious question is, if a world like this existed around S1, could you actually detect it with current tools? The short answer is no, not with JWST. A moon like this would be 10 to 100 times fainter than S1 in reflected light and thermal emission, maybe even more. And it would sit so close to the planet on the sky that its light would be completely blended into the planet's point spread function. At Alpha Centauri's distance, a separation of, say, 1 million kilometers between planet and moon is only a tiny fraction of an arcsecond, far below the resolving power of JWST at mid-infrared wavelengths. The two would merge into a single unresolved source. Could you detect the moon indirectly? Maybe, but not with anything we have running right now. In a perfect world where S1 transits Alpha Centauri A, you might be able to pick up the moon's gravitational influence via transit timing variations, where the timing of each transit shifts slightly as the planet and moon tug on each other. But that requires a very favorable orbital alignment and absurdly precise long-term photometry on an extremely bright star. It's already a stretch. For direct imaging of the moon itself, you'd need a much larger baseline, either a huge single telescope with a mirror tens of meters across operating at short wavelengths, or more realistically, an interferometer, multiple telescopes flying in formation with separations of tens to 100s of meters combined to reach much finer angular resolution. Those concepts exist on paper. Things like space-based nulling interferometers designed to resolve Earth-sized worlds and even exomoons, but they're not flying yet. So where does that leave your Pandora scenario for S1? It's in a strange middle ground. It's not fantasy. The physics of orbits, tides, atmospheres, and magnetospheres all say a habitable moon is plausible around the Saturn-mass planet at 1 to 2 AU from a sun-like star. But it's also not something you can test right now. Even if S1 is confirmed, any moons it has will stay hidden inside the blur of its light for the foreseeable future. You can model them, you can write papers about them, you can design future missions with them in mind, but you can't see them yet. And that sets you up for the last, most frustrating part of this story. You're living right between frames of a cosmic time lapse. You've got one image where S1 exists, two where it doesn't, orbital models that say, wait a bit longer, and a whole generation of telescopes lining up to take the next shot. The only real question now is, when that next window opens, does the dot come back, or does the universe quietly tell you it never there in the first place? What does it feel like to catch a planet in one frame of the movie, miss it in the next, and know the next few frames are already scheduled on the calendar? That's exactly where you're sitting right now with S1. You have a 2024 snapshot where the dot is there at about 1 to 2 astronomical units from Alpha Centauri A, 10,000 times fainter than the star, matching what a Saturn-mass planet should look like. Then you have 2025 snapshots with the same telescope, same instrument, same wavelength, where the same spot on the detector is just noise and speckles, no clear planet signal. You're not at the start of the story anymore, and you're definitely not at the end. You're stuck between frames of a cosmic time lapse, and the next frames are due in the 2026 to 2027 window. The orbital modeling gives you a clear, testable prediction. If S1 is real, and if it's following one of the plausible orbits that link the 2019 ground-based C1 candidate and the 2024 JWST detection, then by 2026-2027, it should swing back out into a part of the image where Webb and the big ground-based telescopes can see it again. The orbital path is not random. For periods around 2 to 3 years, the geometry cycles through hidden inside the inner working angle and far enough out to be detectable on a predictable schedule. That's why people keep pointing to that window. It's not just sometime in the future, it's the next chance the orbit gives you a clean shot. So you really are watching two futures play out in parallel in your head. In the first future, the one every exoplanet person secretly wants, JWST goes back to Alpha Centauri A in that 2026 to 2027 window, dials in MIRI's coronagraph, stacks the data, runs the same careful PSF subtraction, and there it is again. A faint point pops out at almost exactly the separation and position angle you expect from the orbital models. Maybe it's at a slightly different distance, maybe the brightness has changed a bit with phase angle, but it's clearly there, clearly co-moving with the star, and clearly not a one-off artifact. Once that happens, things move fast for astronomy standards. With multiple detections at different times, you can fit a proper Keplerian orbit. That gives you the period more precisely, the eccentricity, and the orientation of the orbit in 3D. You combine that with radial velocity data from big ground-based spectrographs to pin down the mass more tightly. You add in astrometric measurements of Alpha Centauri A's tiny wobble on the sky to cross-check the solution. Within a few orbits, you're no longer waving your hands and saying, Saturn-like, maybe. You're quoting numbers for mass, semi-major axis, eccentricity, and inclination with real error bars. On top of that, you start stretching JWST and future telescopes towards spectroscopy. You look for methane, water vapor, ammonia, and clouds in S1's atmosphere. You try to see how much light it reflects versus how much it emits as heat. You model its cloud decks, its temperatures, its likely storm patterns. The simulations of its possible moon system explode overnight. Groups run thousands of N-body models of Mars to Earth-sized moons packed into the Hill sphere, test which orbits are stable over billions of years, and predict where habitable moons can sit without being ripped apart by tides or thrown out into space. Outside the science community, the story goes mainstream. The planet next door stops being a speculative headline and becomes a real, confirmed world with a catalog entry and a plotted orbit. Every space documentary has to update its scripts. The idea of a gas giant with potential habitable moons 4 light-years away becomes part of how people think about the night sky. The same way Jupiter has moons is just background knowledge now. That's one future, but you have to keep the other one in your head too. In the second future, JWST and the big ground-based telescopes hit that same 2026-2027 window, aim carefully, push down the noise with every trick they know, and nothing. No dot where the orbital models say S1 should be. No faint source creeping along the predicted path. You try slightly different epochs, slightly different angles, instruments in different bands, and you still see only the star's glare and the same old speckles. The follow-up papers in that feature look very different. Instead of "we redetected the candidate and refined its orbit," you get "deep imaging and improved sensitivity rule out any Saturn-mass planet in the predicted region down to a certain contrast limit." The language pivots. The candidate is reinterpreted as a dust clump that didn't survive later configurations, or a statistical artifact that managed to pass the 2024 checks but fails when you stack more data with stricter criteria. S1 joins Vulcan, Alpha Centauri BB, and the long list of Kepler false positives as a useful but ultimately non-existent planet. In that world, the exoplanet catalog moves on. The confirmed planet count doesn't change. The nearest directly imaged giant in a habitable zone stays farther away. Alpha Centauri goes back to being the triple system with planets around Proxima and no confirmed giants around A yet. The hype dies down, but something important still changes. Your understanding of the edge of direct imaging gets sharper. You now have a fully worked example of how a strong-looking, physically plausible signal at the detection limit can vanish under deeper, better data. That example feeds back into every future survey design, every contrast curve, every detection pipeline. So, either way, you're not going back to the old, simple picture of the neighborhood. In one outcome, you add a Saturn-mass planet and its potential moon system to the local map. In the other, you add a very clear warning label. At 10,000 to 1 contrast this close to a star, 5 Sigma isn't as bulletproof as you think. Both outcomes change how you plan future missions, how you interpret borderline signals around other stars, and how you talk about nearby worlds to the public. The deeper point is this. The real story isn't just whether S1 exists, it's that you're even in a position to argue about a Saturn-mass world in the habitable zone of the nearest Sun-like star using direct photons captured in the infrared by a telescope sitting 1.5 million kilometers from Earth. 30 years ago, that would have sounded ridiculous. Today, you're debating whether a specific gas giant at a specific distance from Alpha Centauri A is real or not, based on data and models you can actually inspect. That's the real shift. Whether S1 ends up as a solid world with unseen moons or a mirage carved out of noise and dust, it proves that you've already started exploring the next solar system over with serious tools. You've gone from guessing about other planetary systems in general to arguing over the details of one specific orbit, one specific candidate around the nearest sun-like star in the sky. And the universe isn't done with you. The next JWST cycles, the Roman Space Telescope, the ELT, next-gen spectrographs, future astrometry missions, all of them are going to keep hammering on Alpha Centauri and every other promising nearby system. S1 is either the first giant planet you'll confirm in that habitable zone, or the last big false positive you'll tolerate before your methods get even sharper. So right now, you really are living in the cliffhanger. The dot exists in one frame, disappears in the next, and the next frame hasn't been taken yet. When it finally is, it won't just answer planet or not, it'll lock in what next door to the sun actually means, and how seriously you should take the idea that 4 light years away, there might be a giant world and a family of moons quietly orbiting, waiting for your telescopes, and maybe one day your probes, to finally show up. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.